Okay, so I'm going to open up that script. Again, just go to the workshop website and open the link and copy and paste in. If there's anything that's going to take a while, I will potentially skip it. So we'll see how it goes. I'm going to restart R and start with a new clean environment. And I'm loading in the Bayes move package. The only other new packages in this script are the fir package, which if you saw before, I was using the per package to apply functions or map functions over different list elements. The fir package allows you to do the same thing, but to do things in parallel, meaning they can be done at the same time across multiple cores on your computer. And this is using the future package to do so. And since there's some other helper functions from the future package I want to use directly, I'm calling that in here as well. But this in general makes things run faster than at least they would otherwise, because they don't need to be done in sequence. They don't need to wait for one track to be finished being analyzed. So I'm reading in again these exported results of the tracks from the state space model because it does not account for location error. And as before, if we look at the structure of this data set, date is a character, and we need this to be a date time format. So I am using the as date time function. And similar to the momentum package, I'm using a function called prep underscore data in this case. And I'm giving it the data frame, the names of the coordinates, which in this case, again, I'm using the X and Y coordinates since they're in kilometers already. And then I'm also specifying the ID column. So instead of the prep data function from the momentum package that needs to be capital ID, you can supply any label that identifies the ID column. So if this was PTT or name or whatever you would use, you would just provide that here as a character string. Okay, and let's take a brief, quick look at this. So this is the first 6 rows of this data set, and it added in step for step length, angle, so turning angle. So that's the same as the momentum package. The differences here are that it also calculates net square displacement. So this is the squared displacement from the first location to every other location along that track. And eventually, I think I'm going to modify this later and just only evaluate displacement. So we're going to take the square root of this column. And then we have this column dt. So this is our time difference or our time step time interval. And since we used an 8-hour time interval to regularize our track before, this is in seconds, 28800. So if I was to divide this by 3600 seconds in an hour, that's equal to 8 hours. So that matches up. And then again, since our units for the coordinates are in kilometers, step lengths are in kilometers, and net square displacement is in squared kilometers, essentially. So let's double check our time differences are all at 8-hour intervals. Yes, that is the case. There's only one time interval. And now, normally you would need to potentially filter your data set and like shift times around if it's not at a perfectly regular time interval. But for this example here that we're working through, let's assume that you already pre-processed your data with the state space model and everything's at the same time interval. You don't need to use these filtering functions that are in this package, but the model does require 2 columns called time 1 and obs. And this is just labeling each of the rows. So one column labels the original row number and the other column labels the current row number after removing rows that weren't part of that regular time series. In this case, they're going to be equal. So we're just using this syntax 1:n with open parentheses, meaning from 1 to the number of observations. And this is done with a group by call to ID. So meaning what's the maximum number of observations for each ID. All right. And now we're going to verify that that worked properly. So scroll up to the top of this printout. So we see ID 205,537 and time 1 and obs both start at 1 and they go through 10. And then this next individual again starts at 1 and they all start at 1. So that's good. They didn't start at some other higher number. And then this next line, I'm going to be taking the square root of net square displacement to calculate just displacement and add that to a new column called disp. All right, and now the fun begins. So discretizing the data streams for the model. So like we had to do for the hidden Markov models where you're specifying initial parameters and trying to tell it how exactly it should fit the model to estimate these behavioral states. Instead of doing that, the onus is on how do you discretize your continuous data streams into essentially a histogram that could be well interpreted by this model. So the first thing you should do is always just view like a density plot or a histogram of your actual data sets. So this is our density plot for step length, highly right skewed. Most of the step lengths appear to be below 5 kilometers over an 8-hour time interval. Although there are some larger ones that are even up to about 40 kilometers, likely during a migratory movement. Then for turning angles, we have these two peaks, one at 0 and one at negative pi and pi. And then lastly is our displacement variable where we have a peak essentially next to 0. So these are individuals when they're at the breeding location. And then we have some individuals that disperse about 400 kilometers away and other individuals that are dispersing close to 800 kilometers away. But these are both like dispersing movements where they reach a foraging ground. So we know that there's a couple different peaks based on how far away different turtles moved. All right, so in general, I would say it's easiest to define bins for variables that are constrained between an upper bound and a lower bound. So for things such as turning angles, you have an upper bound and a lower bound. So it needs to be between like negative pi and pi. And how you break that up is your choice. In general, I think breaking up into 8 bins does a pretty good job where there's not too many bins, but there's not too few bins. So that's what I'm defining here using the seek function from negative pi to positive pi by pi fourths. So this will create 2 bins. For step lengths, these must all be positive values, but there's no upper bound. So it's kind of hard to decide, okay, so how do you break this up essentially? So showing this plot again, this continuous distribution, it's like, okay, well, the majority of these observations tend to fall up to 5 kilometers in step length, with a very small proportion greater than that. So let's say, for example, we'll just calculate equal width bins from 0 kilometers to 5 kilometers. And let's say that there's 6 values here. So that's defining 5 bins. So that means that we're going to have these breaks at 1 kilometer, 2 kilometer, 3 kilometers, all the way up to 5 kilometers. And then from 5 kilometers up to the maximum step length, in this case, it's like 42 or something. That 6th bin is going to be our last bin. So these bins do not need to be equal width, but it tends to make it easier for you to potentially evaluate if they are, especially if it is constrained like turning angles. But for step lengths, I'm going to keep it equal width all the way up to 5 kilometers and then group everything else into one large bin. And then for displacement, that one's also a bit tricky because it's multimodal, but it's essentially, it's not circular distribution like the turning angles. So essentially, I'm going to go from 0 all the way up to 800 kilometers here, and then break this up by 200 kilometer breaks. So there's going to be a break here at 200 kilometers. So everything kind of below this is going to be a bin. 200 to 400 is another bin. 400 to 600 is a bin. And then 600 to 800 is going to be another bin. So it's going to be 4 different bins. And we'll see how this works. It might work out okay. It might not. But either way, we can always improve it if needed. So for step lengths, yeah, the maximum is about 42 kilometers. And then here are our bin thresholds or breaks for displacement. So to discretize these data streams, again, this is what you would do if you don't need to filter your data. If your data are being filtered, you might need to apply this function to like a list essentially. But because we didn't, we can just apply it directly to this data frame. We're doing this on the DAT2 data frame object we created. And for providing the step bin or the step length, turning angle, and displacement bin limits as a list in the order that we're providing them in. So we're calling var in here. We're providing the names for each variable. So this order needs to match up across the limbs, var in and var out arguments. So since we're providing step lengths first we say step, then angles are second, turning angles are second. So then we give it the angle column, and displacement is last. So we give it the disp column name. And then we say, what do we want the discretized versions of these variables to be called in our new data set? So I'm going to abbreviate these with SL for step length, TA for turning angle, and capital D disp for displacements. And this should also take a second to run. And now let's visualize these histograms, these discretized data streams. So this is our new step length distribution. It's a little more compacted, and just by looking at the x-axis, you don't know what each bin represents. So it's a little difficult to interpret right off the bat. So we would need to potentially modify this x-axis to label it in a way that makes sense for us and then also for others. Turning angles look somewhat similar here. So we have our peak in the middle at bins 4 and 5, and that represents 0 radians or 0 degrees. And then bins 1 and 8 represent negative pi and pi radians respectively. And lastly is displacement, where we see these relatively coarse bins, and this may or may not work well. We might need to adjust this later on. Okay, and then to be analyzed by the model, it will only accept the columns of these discretized distributions. So if you include like the ID column or the date column, it's just going to crash and fail on you. You just want to give it the columns of these discretized distributions. And it also needs to be provided as a data frame. If it's given a tibble, as I make a comment here, it will also just crash. So just make sure that you're providing it in a data frame format. So like I did with hidden Markov models, you want to set the random seed value. Again, I'm using 1, 2, 3. And then I'm defining some model parameters up here at the front. So I didn't really have a chance to talk about it, but our one main like hyperparameter we're defining for the Dirichlet distribution is alpha. And we're assuming alpha is the same across all behavioral states we're estimating. And we're going to set it low to about 0.1. And this will try to tell the model that there's a high probability that's in one state, most likely. There's a lower probability that it's like a mixture of multiple states to start off. And in general, I recommend setting the parameter here I'm calling n Gibbs. This is the total number of Gibbs sampler iterations for this Markov chain Monte Carlo algorithm to 10,000. I recommend maybe starting at 1,000 or 5,000, just because the quicker it runs, if it breaks, the quicker you can fix it. If you have to wait 30 minutes or an hour for it to run and then realize it broke, it's going to take you forever to like diagnose these things. So let it fail fast so you can have it run fast. And then you can increase these iterations after the fact. So we have alpha and Gibbs, and burn is our burn-in period. And I'm just going to call that half of the total number of Gibbs iterations here, but it doesn't necessarily need to be. And then I'm also defining what I'm calling Nmax clusters. So this is the number of maximum clusters or number of maximum states that I think are possible. In general, it might make sense to make this like 50% to twice as large as the number you think might be present. So let's say I think there might be 3 states. Maybe make this, in this case, 6 or 7 states, all the way up to maybe 10 states at most. You don't need to put in like 20 or 30 states because there's no way our model is going to find that from these data streams. But if you're working with like only step lengths and turning angles, or maybe 1/3 variable, at most you would only do like maybe 9 maximum clusters or states. And then I'm providing those to this function called cluster obs. So cluster obs is what's running this M3 model. So it's clustering the observations directly into behavioral states. And this says it should take 2.5 minutes to run. And it has this print out progress bar here. So at least you have a sense of how far this model is along in its progress compared to the total number of iterations, the percentage, and then how much time it's taken, how much is elapsed, and the estimated how much is remaining, which is always nice considering that plenty of other models will not give you anything like that, and you have no idea how long it's going to take to run. So I think that's a nice feature to have. And in general, it used to be the case, at least, that the Bayesian state space models would take potentially hours to days to finish running. Whereas now with foie gras, it takes literally seconds to run. So this isn't necessarily as much of an improvement on state space modeling in terms of speed, but compared to what you might be running with a hidden Markov model, if you have like a large data set. So if I use the raw data instead of the 8-hour predicted data, it might take a hidden Markov model like 10 minutes to finish running with like 30 retry fits. Whereas for this one, without needing to do that, it might take a couple minutes. So the larger your data set is, the bigger computational gains you get from running these types of models potentially. All right, it says there's about 30 seconds left. And then we'll look at the diagnostic plots and see whether the model actually converged or not. And the nuance with this type of model compared to maybe other Bayesian models you may or may not have ran before, where you're often looking at trace plots and density plots and autocorrelation functions or other things to assess model convergence, is at least for the M4 method, not maybe so much with this method, we essentially remove a lot of these other extraneous parameters. So the only way to kind of evaluate whether the model converged is to actually plot the trace plot of the log likelihood itself. So it's a bit different compared to like what you might use with, like if you use JAGS or STAN or something else like that. Because this is like a custom Gibbs sampler that we created. Okay. So now let's look at the trace plot of the log likelihood directly from that model fits. And what we're looking for is it to reach an asymptote essentially. And I didn't plot this next line. So the red vertical line is showing basically the end of our burn-in period. So we want everything after the burn-in period, so everything to the right, to basically be a flat line that's reached an asymptote. So this indicates that we've reached our posterior distribution, and it looks like a fuzzy caterpillar, which is kind of the technical term that's used for investigating trace plots in Bayesian models. So to me, this looks like it's good. It looks like it's converged on the posterior distribution. So now that we've checked that trace plot, we want to essentially consolidate all of our posterior estimates. So I'm going to define here the indices for the posterior distribution. So everything after the burn-in period to the last iteration here, I'm going to call post-seq. And then I'm going to extract these estimates from the model for these indices. So we have our object theta, our matrix theta, And I'm going to calculate the mean value for each column. So what's the average probability of being in each state across all observations? And if we look at this printed output for state 1, this first column, it's going to represent about 72% of all observations. And state 2 represents about 15%, state 3, 7%, and so on. Whereas these last states don't represent much, if anything. And then we can also look at the cumulative sum of these. And a general rule of thumb that we've used in some of our papers is that essentially the states that add up to represent 90% or more of the observations are probably the most likely states that are actually present. But ultimately, you also want to look at the state-dependent distributions of each variable to see if they make biological or ecological sense. So if we look at what's the number of states that at least reach that 90% threshold, it appears that by the third behavioral state that it was estimated, that passes or surpasses 90%. So I'm assuming most likely 3 states. There's the possibility there's a 4th, but we won't know that until we plot these state-dependent distributions. And I'm doing so using this get behave hist function and supplying these names for each of the movement variables. So this is getting the bin values from that phi matrix I mentioned in the slides, and then changing the behavior number or name to a factor. And this next set of code I'm using just to make more informative x-axis labels. So I'm just going to kind of jump through that to save some time, and then make a plot of these distributions. Okay, so each row is representing a different behavioral state. So we said there was up to 7 maximum possible states. So the model estimated up to 7. Based on that theta matrix we investigated, it appeared that maybe there was 3 states that were likely. But after visually inspecting these plots, it appears that actually it seems like there's probably 4 behavioral states present. So unlike what you would potentially do after the fact with hidden Markov models, because you're saying up front what you think the behavioral states are and how they're defined, in this case, you get your results and then you look at them row by row and say, okay, I think this is what state 1 is. I think this is what state 2 is. So state 1 is defined by very low displacement, so ranging from 0 to 200 kilometers. Everything above that is in low proportion. Step length is also very small, from 0 to 1 kilometer, is the majority of these. And then turning angles are relatively flat here. So maybe a little bit more at negative pi and pi, but everything else in between is lower. The second state has relatively higher displacement. So anything in these last 3 bins ranging from 200 to 800 kilometers away from Fernando de Noronha, and step lengths are a little bit higher than this first state, but not a ton higher. And turning angles are very similar to state 1. So again, it's either moving every direction equally, or maybe moving some straightforward, some turning around. This third state is, again, it's not leaving Fernando de Noronha, so displacement is essentially 0 or very small. Step lengths is actually a little bit higher potentially, or about the same at least as the second state, but turning angles are like entirely at negative pi or pi. So it's a constantly turning around. And then this fourth state shows intermediate displacements. So there's some individuals that aren't really moving that far away, whereas the highest proportions are in the second bin from 200 to 400 kilometers. But step lengths here is the highest bin and the highest proportion. So it's moving very fast. And then turning angle is almost entirely at 0 radians. So it's moving very straight. So just initial breakdown based on what we think this could represent. The first state is staying at the island it's moving very slowly and turning around a lot, or just at least a bunch of different directions. So this may be like an area restricted search pattern where the animal might be foraging, but staying at Fernando de Noronha. The second state has displaced from the islands. It's still moving around a bit faster, but it's still also turning a lot. Highly tortuous, so this is probably a foraging behavior at the mainland. This third state is also at the island with larger step lengths, but is turning around much more than this first state. So this might be like a highly encamped state where it's not moving at all. And this fourth state has intermediate displacements, but then very high step lengths and turning angles around 0. So this is likely that migratory state. So that's what I'm kind of getting from. But if you were to say, okay, well, maybe there's a fifth state here. Displacement is up at this up topmost bin. Step lengths are higher, but they're not quite as high as this fourth state. And these turning angles are at pi and negative pi. But in general, that doesn't quite make sense to me. Why would it be turning around rapidly while also moving quickly? And since this is in such low proportions, like 2% of all observations, it just doesn't make sense to include this as a possible state. And then these are just a mix of bins that are like completely flat or that the values don't really match up well. So 6 and 7 wouldn't even be in consideration. But this is like a process I would work through for deciding how many states are probably there and then interpreting what they represent. So my comment here, it actually looks like there's 4 states instead of 3 states. And then to assign these behavioral states, we're going to get potentially different ways to approach this. So I'm going to take these estimates z posterior. So these are our state estimates from the posterior distribution from this model fit, and call these z post. And then I think this code was from a previous version that I was running with these data sets where I was combining different states together. We're going to skip that and move on to this next line where I'm calculating the proportion of samples from the posterior distribution assigned to each state. So like across all iterations of the Markov chain, what's the proportion that it was assigned to one of these 7 states? And I'm defining here a threshold as one possible metric to classify the states. So for the hidden Markov models, it says, okay, this is the state it is. So there's some other helper functions that show that you can estimate the probability it's assigned to a given state. But essentially what most people use and what it gives you directly is like the most probable state. So that could be 54% of the time it's in that state, or it could be 99% of the time. But without inspecting those probabilities, you wouldn't know that. And this does that a little bit more explicitly, at least in this one method. So I'm defining a threshold saying that if an observation is attributed or assigned a behavioral state 75% or more of the time, then I'm highly confident that it is actually that state. If it's assigned to a given state less than 75% of the time, then I'm not sure what it could be. It seems uncertain, so we're going to leave it labeled unclassified. So that's what I'm calling z post thresh, because I'm using a threshold metric to define what the behavioral state is. And if it doesn't exceed that threshold, I'm just going to label it NA here. Another way you could do this, like with the hidden Markov model, is to say what's the maximum probability. And I'm going to assign the maximum probability to that state. So if there's like 5 states that are possible and one is represented 30% of the time and the rest are less than that, even though it's only 30% of the time of these iterations in this Bayesian model, that's the maximum. So that's where we're going to assign it. And alternatively, for the Bayesian approach, there's what's called a map estimate, or the maximum a posteriori. And that's essentially the peak of like a distribution from like a Bayesian posterior distribution. So that's like what has the maximum likelihood essentially, but the Bayesian version of that. And that's defined in this z.map object from the fitted model. So that's also another possible way to inspect or investigate the estimated behavioral state. So with that, I'm going to now add these 3 different ways to assign the behavioral state to these observations. And I'm now going to add these back in, and we're going to visualize these results. So I'm going to say that there are 4 states. If the model or these columns say that there's a value greater than 4, I'm going to set it to NA, just so it ignores them. And now I'm going to give them names here. So that's what I'm doing for these variables or these columns labeled zmap, zpost_thresh, and zpost_max. Is whenever it's equal to 1, it's called breeding encamped. So it's at the breeding location, but it's in an encamped state. If it's equal to 2, it's in a foraging state. If it's equal to 3, it's in a ARS state at the breeding location. And if it's equal to 4, it's migratory. Anything else that's potentially missing is unclassified. And then I'm specifying the levels and creating a factor instead of a character. And then we can look at the proportions of each behavioral state. So summarizing for the map estimate, about 67 or 2/3 of the time, these observations are assigned to the encamped state for the breeding location, and about 3% of the time is migratory. Compare that to the threshold metric, and also we have 2% of the time it's unclassified. For threshold, we now have 15% of observations are unclassified. So that just means that we're not considering them, but that's not too dissimilar, I think, from the BSAM package for state-space modeling, where you had a gamma value, and typically what was commonplace is anything between the values of 0.25 and 0.75, those were considered unclassified. So this is a similar way of denoting that. But breeding encamped is almost in the same proportion. Breeding ARS is slightly lower because we probably lost some observations that were labeled as unclassified. Foraging is now about 10%, whereas previously it was about 23%. So that also lost a lot. But then migratory stays the same because it's highly confident about these migratory behaviors. And then the last one is the maximum proportion. And we see that there's more assigned to this encamped state. And some of these have been slightly modified with still some unclassified behaviors, but not as many as the threshold approach. And now let's map these. So I'm going to load in again that Brazil spatial vector layer from the R Natural Earth package, and then use ggplotly here to interactively plot this ggplot code. And I'm labeling these points based on the behavioral states. So if I zoom in, these red triangles are representing the end of the track, and the green circles are the start of the track. So we see here in yellow, this is migratory, whereas gray is unclassified. If I zoom into this foraging area, it's labeling these as in foraging. Some are migratory once in a while, and then there's a handful that are still unclassified, but I think it does a pretty good job. Let's say we go to the island itself. So we see some red triangles indicating the individuals that are residents. And we see some labels that are foraging, actually, even though it's not displacing anywhere. A lot of breeding encamped, a lot of breeding ARS. So it's doing an okay job here, but there's definitely room for improvement. But then obviously everything kind of in between these migratory phases of the movements are almost entirely labeled as migratory, and sometimes there might be something labeled something else, like this one observation labeled foraging. So that's using the map estimates. If we use the threshold estimate, this posterior, again, we see these migratory phases identified pretty well. But one thing you will notice is when I zoom in, there's a lot more unclassified behaviors. And that's because it looks like this individual is slowing down, but it doesn't know quite which state it might be. It could be migratory, it could be foraging, it could be something else. So it's definitely not considering we're not labeling as many of these observations. And then lastly, using the maximum value from the posterior, this is going to represent probably something more similar to a hidden Markov model, where essentially there's very few missing values, at least for this Bayesian model, but almost everything is labeled. And this resets. All of these observations in between are labeled migratory. So it seems to do a decent job. But again, this model is not accounting for any kind of temporal autocorrelation. So I'm sure there's definitely some room for improvements that is definitely present in these tracks. But it does a pretty good job here for this example. And you could do the same thing using that shiny tracks function from the Bayes move package. I'm just going to skip that for now in the interest of time, but that is the M3 model and kind of the process you'd go through for fitting that. But now I'm going to move on to the M4 model. This is estimating segment level behavioral states using this mixed membership model. So we can still keep our discretized data sets, but now I'm going to use this df to list function to break this up into a list by ID, which I'm going to call dat.list. And then from this, I'm going to only keep the columns labeled SL, so step length, turning angle, displacements that are discretized, as well as, at least in this case, the ID column. So the ID column is included for the M4 model. But again, the structure is a list. So if I was to open this up, dat list sub, we see there's a list of data frames where each element is a different ID. And that's how we need to give it or feed it into this model. And that's how it can run this model in parallel. So this is using the unsupervised version. We're letting the model decide the breakpoints on its own. We're not going to tell it anything. And in this case, I'm going to set the random seed again. Leave the alpha hyperparameter as 1 or just uninformative, so it assumes everything's equal. And n Gibbs, I'm going to be setting in this case to 50,000 iterations. And one thing I need to supply in this case is the number of bins. So this needs to be the bin number as these columns are placed in order. So since I have step length first and turning angle, then displacements, I need to provide these numbers of bins in that order. So there's 6 bins for step length, 8 bins for turning angle, and 4 bins for displacements for this model. So I'm going to run those. Next is where I'm going to set up essentially a progress bar that I want to print out. And then I want to say that I want to run my model in parallel using the future package. So that's what I'm doing when I set it to multi-session. And then the workers, or the number of cores I want to use, is the maximum number available on my computer, but I don't want it to crash. So ideally you want to leave at least 1, if not 2 cores open to do other things that are working on your computer. So in this case, I'm saying available number of cores minus 2, which in my case, I think is 10 cores. And then you would run, instead of cluster obs, the function called segment behavior. You give it this list we just made, then the number of Gibbs sampler iterations, the number of bins in this concatenated vector, and then the value for alpha, the hyperparameter. And it should take about 27 seconds to run. But because it's evaluating a list, it doesn't know how many iterations or how long it's going to take per list to finish. So instead of providing estimates on like how much time is left, unfortunately, all you get is a progress bar. But at least that's still something. You get some index of the progress of your model. And we see here that it's starting to wrap up. All right, so about 30 seconds. That's not bad. And in general, I think it's probably good practice to reset the way your computer is working after running this, because sometimes if you run the plan multi-session multiple times, it'll like confuse your computer and it won't work properly, or it might have some issues with memory. So I recommend running afterwards, running plan and then sequential. And that'll change it from running in parallel to running sequential, which is the default for your computer. And we can always change it back for the next model. So similar to the M3 model, for M4, we're also only going to evaluate the likelihood. In this case, it's the log marginal likelihood. And this will make a different likelihood plot per individual, since each individual is analyzed separately. Okay, so this is the first 4. And it's important to pay attention to the scale on the y-axis here. So the x-axis is the iteration number. The vertical red line is their like kind of index for our burn-in period. So we want everything to the right of that to be relatively flat and looking like a fuzzy caterpillar, which isn't always the case for likelihoods, a trace plot of likelihoods. But we see that the scale here is relatively small. So this whole range is like 60. So if you were to increase this to like 1,000, this would essentially look flat here, which might be the case if you were to have a model that covers a whole much larger range of space. This one only covers a range of about 20. So even if you see some of these like peaks or dips here that might otherwise be concerning, that's only a result of the scale we're visualizing this on. This is only a scale of like 15 or 20. So just because it doesn't look as smooth or as fuzzy as maybe the previous one looked, that's not concerning in this case. It still looks like it's hitting an asymptote and staying there. Same goes for this last individual here. Although the scale is larger, this is about 200, and we see how flat that looks. Another thing you can inspect if you want to, that might be of some value, although it's not required, is looking at the change in the number of breakpoints estimated by the model. So like I described for how this works, each iteration is predicting a different set of breakpoints. So whenever that stabilizes, you would hopefully assume that that means that the model is converged on the posterior distribution. So if I show this, it's a bit messy, but we see that in general for this first individual in the top left, it appears that it's typically estimating 3 breakpoints, although it jumps to 2 and to 4 pretty common or pretty frequently. Same for this next individual in the top right, whereas these bottom 2 are almost entirely estimating only 1 breakpoint and occasionally estimating 2. So these are 2 resident individuals that aren't moving anywhere, whereas the first 2 are migrating, and then our last individual is also migrating, and shows that there's likely 3 to 4 breakpoints probably occurring. And the one nuance of this type of model is that because there's different numbers of breakpoints, and breakpoints occur at different locations on each time series, each track, that we can't like average them together or something like that you'd normally do with a Bayesian model. So what we do is take the map estimate, which I said before is essentially our best guess, our best estimate from the whole model. So we're going to say that hopefully that best estimate, the highest likelihood, will result in the best breakpoints that break this track up. So if we were to run this model in a semi-supervised fashion, where we're going to pre-specify some breakpoints, we could do that as well. So the way I'm going to show that here is essentially for this object dat list, so our list of our different tracks. We're going to try to identify when we're either in this breeding location phase, the migratory phase, or the foraging phase at these mainland locations. So this is saying if displacement is less than 6 kilometers, we're going to assign it to maybe state 1 potentially. If step length is greater than 4 kilometers, then maybe it's in state 2. And if displacement is greater than 6 kilometers and step length is less than 4 kilometers, then we'll give it a state of 3. So this is related to state 1. That's probably they're staying at Fernando de Noronha at some point in time. State 2, they're moving quickly, and this is probably them migrating. And state 3 is they're far away, but their step lengths are small, so they're probably at a foraging ground. And this is all just like a priori looking at the values and trying to come up with some insights on your own. Ideally, you'd have like a variable that might be, in this case, right, let's say Argos tag knows when it's dry, when the animal hauled out, if it's air breathing, or if it's underwater. So then you'd have a binary variable. It's either 1 or 0, or maybe it's a category 1, 2, 3, 4. So whenever that value changes, that's when you can identify these shifts. In this case, I'm essentially making something up based on prior knowledge of these set of tracks. But what we come up with is this plot. So this is essentially identifying beforehand, before we even run the model, a potential resident phase, a migratory phase, and a foraging ground phase. So this is all just using metrics, basically. But this is helping me identify potentially where breakpoints may occur in breaking these time series up. So that's how we're going to think of this. So I'm going to use the map function from the per package with this find breaks function from the Bayes move package. So we want to say, where are the breakpoints in relation to this phase object or this phase column variable that we just created. So whenever the value changes from like what we call phase 1 to phase 2, when does that occur? And that's what we're going to use as our pre-specified breakpoints. So if we look at these values, so the first individual has a large number of potential changes. The second one has even more. 3 and 4 are resident individuals, essentially aren't changing at all. They're staying in that phase 1. And then our last individual does have some changes. And this is likely more changes than our presence, but this is at least a place to start. And if you pre-specify your own breakpoints for your own data, you may have much fewer. So these likely aren't going to be the final breakpoints, but again, it's a starting place for the model to consider. But the one thing the model requires is that every track must have at least one breakpoint. So even if there's only one track segment that's truly there, it can't have 0 breakpoints. It has to have something. So in this case, if there's a object here, so our 2 resident individuals that don't have any changes, we're just going to give it a value of 1. And this could be any number, essentially, that's up to the length of the total number of rows for that individual, the number of observations. Ideally, something at the very beginning or the very end of the track. So in this case, I'm giving it the value of 1. So now when we look at these, our 2 resident individuals have 1 breakpoint, which I've labeled 1 for the index. All right, and we're going to run again now. The same parameters here in the beginning, but the difference is going to be in our model call to segment behavior. We now provide an argument called breakpoints, and I'm giving it the breakpoints we just pre-specified to see if that helps improve the fit. So this should also take only about 30 seconds. And in general, the larger the number of bins you're using, the larger the number of variables, that will increase the runtime for your model to finish. All right, so that's done. Let's check out the trace plots for each individual. Okay, so these top two look like they probably converged. When we look at these bottom two at first glance, they're all over the place. But again, make sure you check the y-axis. For the one on the bottom left, this is a range of 8. So that's essentially nothing. For all intents and purposes, this is flat. On the right, the same thing. It's a range of 8. So you might as well consider this flat. So it appears to have converged. On the posterior, and for our last individual, again, this also appears to have a small range. So up to 40, 45 at most. So I think these all look pretty good to me. I'm going to skip the trace plot of the breakpoints for now. So get through this quickly. But once you've run your model, whether you pre-specify breakpoints or not, the next thing you need to do is get the breakpoints for the map estimate. So again, the highest likelihood estimate from your posterior. And to do that, use the get map function. So you supply it for dat, the log marginal likelihood, or LML, from our fitted model. And then you also tell it the burn-in period. So it knows to only consider breakpoints after the burn-in. And for large data sets or long Gibbs sampler iterations, this could take a little bit, but not too long. And then once it identifies the map estimate here, so this should be basically like an index for each of these list elements. These are all about 20 to 30,000 roughly. Now we can get our breakpoints. So the values that have a 1 at the end is our initial unsupervised model. If it has a 2, that's from our semi-supervised model. And then now we're going to actually look at the lengths of the number of breakpoints per individual based on these two models. And we can see that they actually have the same number of breakpoints estimated per individual. So they could have different positions of these breakpoints, but right off the bat, it seems like they're working pretty similarly. So these breakpoints we pre-specified may or may not have helped. To do that, we're actually just going to print these breakpoints in our console. So for the first individual, we see that 4 breakpoints again were identified, and these are at time indices or observations 275, 285, 293, 310. And if we go to the semi-supervised model, it's the same exact indices. So if you go down the row per ID and then across the breakpoints to compare these outputs, they're identical. So essentially meaning that the segmentation model was essentially unchanged from the model, the breakpoints we pre-specified, which at least for this purpose is a good sign that we reached our best fitting model. So we didn't learn anything new by pre-specifying breakpoints. The model was able to do it successfully on its own. Okay, once you identify the breakpoints you want to keep, so in this case, we can just keep the breakpoints from our initial unsupervised model. We're going to plot them using this function called plot breakpoints. And there's a couple different ways to do so, which I'll demonstrate. Essentially, you'll give it that list you started with, which I call dat list. And you can specify whether you want it on the x-axis to be a date time format or like the row number or observation number for each track. And you also tell it which of the variables you want to plot on the y-axis, so your data streams. And this can be done with either the discretized data streams or the continuous data streams. And then tell it the names you want to give to each y-axis label and the breakpoints you want it to plot along the time series. So for this case, I'm using date is true, and I'm plotting the continuous variables. So for this first individual, this one that migrated, we see that displacement here is essentially 0 all the way up until sometime about in March. And then it shoots up here and migrates and then reaches a foraging ground and stays at this far off distance. And there's 4 breakpoints that kind of break this up here. So obviously these two breakpoints make sense in capturing the migratory period, but then there's these two other breakpoints a little bit earlier on that seem to be picking up something, but it's hard to tell from just displacement alone what that might be. If we look at step length in the middle, again, it seems to match up pretty well with this migratory period. And there are some peaks here that might be occurring that seem noticeable here for step length, which is why it was estimating these breakpoints at these locations. And turning angle is showing essentially a lot of noise. It's always kind of hard to tell for turning angle, I would say a lot of the time. But it's probably step length that might be driving these two other earlier breakpoints. We look at this next individual, we see some other types of breakpoints. So we see this migratory period is actually broken up into two segments, and then this foraging period is broken up into two segments, which seems unusual. And if we look at the step lengths, it seems that this second or third segment makes sense because step length is dropping precipitously. So it's slowing down as it's getting further away before it reaches the foraging area. And then this last breakpoint is estimated because step length went from being probably from like 5 to 10 kilometers to lower than probably 0 to 3, 0 to 4. So this change in step length and maybe even turning angle here is what's impacting the estimate of this last breakpoint. Once we get to the resident individuals, we see that it's just a continuous kind of low noise for displacement, step length, and turning angle. There are some things here, but it's not enough of a change for a long enough period of time that it has to put a breakpoint somewhere, so it puts it at the very end of the time series. So that's essentially what you would see almost every time if it's not identifying like real breakpoints, is it just puts it at the very end, at the very beginning, and says this is fine. Same thing for this other resident individual. This breakpoint's a little bit off the left end, but essentially saying that this is just one segment. There's not multiple phases of behavior happening. And one thing that might be hidden if you're looking at these continuous variables is that the model didn't consider continuous variables, it considered discretized variables from these. So just because we identify breakpoints, they may not match up with what we'd expect based on looking at these time series of continuous values. So if we actually look at, whoops, forgot to do the last one. If we look at the discretized distributions over time instead, so on the x-axis, time is now just the row number, and then instead of the actual value for each of these movement variables, it's the bin number. It actually seems to make some sense in terms of where it's highlighting some of these changes, although at least in this particular individual, there's nothing major changing in our interpretation. We still have this large shift in the displacement during this segments. Can't see anything going on in these earlier ones, but this is likely due to the step length. And you can go through each of these others. So like for this individual, it's almost like a staircase here of changing in displacement. So there are things here you'd probably want to take a look at, especially if you're getting breakpoints that don't match up with what you'd expect. Same goes for these resident individuals, and I'm just going to move on past this. Okay, if you see these warning messages, this is just due to the new syntax used for ggplot, which I haven't updated in the package yet. So it still works fine, but you might just see these warnings. But it seems like to maybe improve some of these breakpoints, I want to slightly redefine how I'm binning my data. So if you're ever unsure about the breakpoints, they don't match up with how you'd expect based on looking at these time series plots, the first thing you should always go back and do or modify is adjust these breaks or the way you discretized your data set. So I'm going to look at the distributions again for step length and for displacement. So for step length, I'm going to change this slightly So I'm going to now define a additional bin. So I'm going to go from 0 to 5 at equal bin widths. So 1, 2, 3, 4, 5. And then everything from 5 to 10 kilometers is going to be another bin. And then 10 kilometers to 42 is going to be the last bin. Whereas for displacement, instead of going by increments of 200, I'm going to go by increments of 150 and see if that helps. So in general, adding more bins helps to kind of increase the resolution of identifying these changes. And that's just showing the new bin limits. So we need to rediscretize our data sets using these new step and displacement limits, which are now have these twos at the end of them. Turning angle bin limits are going to be kept the same. And these are our new distributions. So we see for displacement, it's much different. It's not as smooth. So it's identifying these gaps that were more clear in the continuous density distribution. And now doing the same thing as before, subsetting the columns I need, setting the random seed value, setting up these model parameters, changing the number of bins for step lengths and turning angles, and then setting up the progress bar and making it as parallel to run. Again, this should also take about 30 seconds. It's just about 5 o'clock, so I'm going to try to wrap this up pretty quickly and get to the final guidelines and recommendations. Definitely running a bit longer than I anticipated. Yeah. All right, starting to finish. Okay, so do a quick plot of the likelihood. And again, I think these all look pretty good to me, especially when you look at the y-axis and the scale of that. And same goes for this last individual here. All right, so now, again, I'm going to get the map estimate and then the breakpoints associated with the map estimate and compare it to our initial breakpoints. And we see that there's fewer in some cases. So initially, we had 4, 4, 1, 1, 5 for the breakpoints for each ID. And now the first individual only has 3 now, and the last individual has 4. So that's a little bit of a change. And if you look at the positions of those breakpoints, sometimes they're slightly different. So in this case, this first individual has a breakpoint at index 294 or rodent 294, whereas for the first version, it was at 293. So it's a slightly different version, but it's identifying roughly the same breakpoints, but maybe fewer of these slight shifts that may not be real signals. And then we can plot these again, these breakpoints, and I think it does a pretty good job here. So identifies only a single period here just before that main migratory movement where step lengths increased for this first ID. The second ID essentially only identifies this one large migratory movement with maybe a small pre-migratory phase, and then still breaks up this last foraging period into a segment where it's moving a little bit more quickly versus not moving much at all. The 2 resident individuals are essentially unchanged. They only have 1 breakpoint. And then this last individual has fewer breakpoints than before, but they characterize these changes better. So we have this displacement phase that's rapidly increasing, and then it slows down a bit, and then it's relatively flat here. And that's shown also similarly with their step lengths and turning angles and how those change. So that's all very reassuring. And again, you could do the same thing with the discretized versions of those variables. So once you're happy with that, you would use the assign tseg function to assign these estimated segments, now these track segments, to each observation. So whether it belongs to segment 1, 2, 3, however many segments there are based on these breakpoints we just estimated. And now we have our data sets with all these columns. And at the very end is this new column called tseg. And this is the segment number associated with each individual turtle. So that's the first stage of our model. The second stage is the clustering stage, which is going to cluster these segments together into states. So first, we're going to subset this data frame we just put together, and we're only going to keep the ID, the segment number, and then these discretized data streams. And we're going to call this dat_seg2. We're again going to define the number of bins if necessary in order, and then use the summarize tsegs function to essentially summarize the number of observations per bin per time segment for each data stream. And that looks something like this. So each row is a different time segments with an ID label. So for the first ID, the first individual, there's only 4 time segments. For the second individual, there's 5 time segments, etc. And on the columns, we see y1 dot 1, 2, 3, 4, 5, 6, then y2, y3. So the y1, y2, y3 is step length, turning angle, displacements. And then the number after that decimal is the bin number associated with it. So we have 7 bins for step lengths. Then it starts over at turning angles 1 through 8. And then displacement y3 is 1 through 5. And this is the number of observations in each of those bins. So this is preparing this summarized data for our LDA model. Again, setting this random seed number to make it reproducible, and defining our model parameters, so the number of Gibbs iterations, the burn-in period. We're defining, again, the Nmax cluster values, the maximum number of behavioral states, and then the number of data types or data streams, which in this case is 3. And setting our hyperparameters on the priors. So in this case, gamma for the truncated stick breaking prior, we're setting to 0.1, and then alpha for the Dirichlet prior is going to be 0.1 as well. And we're going to use the cluster segments function in this case to cluster these segments together, as opposed to the cluster obs function that was used to cluster individual observations together from M3. This takes 19 seconds to run roughly. And everything after this is going to be very similar to M3, where we're going to look at the trace plot, then look at the distributions and try to interpret the behaviors from that. All right, and it's done. So we'll look at the trace plot of the likelihood. It looks nice and flat here after that burn-in period. So everything appears to check out there. Next, I'm going to use this extract prop or proportion function to get the proportions of behavioral states per track segments, called theta stim for our theta matrix. And then I'm going to summarize this a bit and kind of rearrange it so that we can visualize the proportions associated with each of these track segments. So it appears that obviously there's a large proportion that's in state 1. That's the most common, then state 2, state 3, etc. So there's probably at least up to 3 states, maybe 4 states, and it's doubtful there's 5, 6, or 7 states. If we calculate the values for each of these, the average proportions, we see it's 47% roughly for state 1, 22% for state 2, etc. And taking the cumulative sum we only crossed that 90% threshold after 4 states here, where it jumps from 85 to 95%. So it's possible or probable that there's about 4 states that are present in this data sets based on these segments that we created and fed the model. So again, we're going to use this get behave hist function to extract these state-dependent distributions from the phi matrix, and again, define the x-axis labels properly, and then plot our results. Okay, so what we have here is the 7 different possible states, which are these rows, and then our columns again are these data streams. And I've highlighted or colored 5 states, indicating that there's potentially likely 5 states that are present. So here we have for the first row, displacement is all in this first bin. So it's at the island. Step lengths are really small, turning angles are relatively flat. So this could also be that kind of breeding ARS state that we identified from the M3 model. The second state is relatively flat displacements, high step lengths and turning angles near 0. So this is probably that migratory period or behavioral state. State 3 has displacement only in this middle bin with intermediate step lengths and kind of flat turning angle distribution. So this seems really particular to at least one individual or 2 individuals that only went about 300 to 450 kilometers away to the foraging ground. And state 4 is displaced the furthest and has slightly different distribution of step lengths that are intermediate to states 1 and 2, but has the similar or the same distribution of turning angles as state 3. So ultimately, I think we can actually lump state 3 and 4 together and say these are foraging behaviors just at different distances from that initial breeding ground. And then state 5 is showing displacement that's close to the breeding ground, moving a little bit faster than state 1, but turning angles are really high typically. So near pi and negative pi. So it's turning around a lot, and this is probably like an ARS state at that breeding ground. So if we lump states 3 and 4 together, I think we've identified something very similar to our M3 model. So that's what I'm going to do essentially in this case, moving forward, is I'm going to attribute these behaviors or assign these behaviors from the segments to each observation. And then now plot these. So we're looking at the proportion of each behavioral states over time per segment. In this case, I have the foraging states separated, but essentially you can consider these the same or together. So initially they're all in this breeding and camped states, and then there's this shift where some of them, 3 of them, undergo a migratory period, and then they enter a foraging period, whether at closer areas or further areas from that that breeding ground. And now if I assign these behavioral states back to our original data set using these proportions from the track segments, we can look at maps of these tracks with the associated behavioral state annotations. So we see for some of these individuals that we have these migratory periods that are well classified, and then other periods essentially at the beginning are foraging or some form of breeding or encamped or ARS behaviors. The resident individuals are labeled entirely as this breeding encamped, essentially, at least for what's easily visible here, although it's likely a mix of the encamped and ARS states. So this model seems to be doing a pretty good job here. And unlike the M3 model, it's accounting for some of this temporal autocorrelation in these behavioral changes. And alternatively, you can make these plots, but show it as a probability or proportion of each of these different behaviors. So if you said, what's the proportion of being in the migratory period for all these individuals, I can show this in this new color ramp where the more yellow it is or closer to yellow, the greater the probability that it's in a migratory state. The darker it is, the less likely it's in a migratory state. You combine the foraging states together, you can do the same thing for foraging. So everything kind of here near the islands and the migratory period is dark, meaning there's a low proportion of foraging. Everything near the coastline is higher proportions of foraging. All right, so that is it. That does it for this presentation on the non-parametric Bayesian models.